Alright, so one of the questions we have was starting with toluene in two different scenarios. This is from Sapling, I can't remember exactly what question it is. But toluene. And what they're going to do is they're going to show how essentially the order of steps matters on the relationship of where things will end up on the ring, right? So right now in both cases we have toluene. So the substituent on the ring is a methyl, and that's an activator, right? Because of hyperconjugation. Now, what do you know? All activators direct where? They direct which direction? To which position? Ortho, meta, or para? Activators all direct the same place. Activators, all activators direct ortho and para. Most deactivators direct meta, but not all. But all activators direct ortho and para. So this is an activator. It should direct ortho and para. So I'm going to modify this a little bit differently from the one from the homework, just to make it a little more interesting. And what we're going to do I'm going to give you the product for each. Okay, so the product for each of these is a carboxylic acid with a bromine. So it's a two-step process. I'm telling you it's two reactions. The question is going to be, what is the right order of these reactions? That's what you got to think about. Right? That's what you have to think about. So, first we got to analyze what's on the ring, right, of our products now. So we knew from our start materials, these are activators. The methyls are activators, so it's going to direct ortho or para. But now if we look at our products, we have different substituents. Right? We have different substituents. Both the carboxylic acid and the bromine are what? Are they activators or deactivators? They're both deactivators. But, right, this carboxylic acid is a deactivator, but which way does it direct? It directs ortho, meta, or para. This deactivator directs meta. Right? This bromine's a deactivator. Which way does it direct? Ortho and para. Right? So that's something to think about. Now we should look at the relationship between these two things. This carboxylic acid and this bromine are what to each other? They're both para to each other. Right? They're para to each other. This carboxylic acid and this bromine are what to each other? They're meta to each other. Right? So now we got to think about, well, wait a second. These two things are meta to each other. Which had to come on first? Which had to be in place first? The carboxylic acid or the bromine to get this meta relationship? Which had to be there first? If the bromine was there first, it would direct ortho or para. So what had to be there first? The carboxylic acid. Right? So the first step here is KMNO4. The other option you could use, or some sort of chromium source. If you see chromium, that's another thing that does that benzylic CH oxidation. Right? We have benzylic CHs here. So that would put a carboxylic acid there. Right? So that's step one. After step one, we'd have this. Now to get to step two, since the carboxylic acid is a meta-director, we need to use what? We need to use Br2 and FeBr3. And that will put the bromine meta to the carboxylic acid. Okay, so now that we have this one done, we notice this meta relationship. Now let's go back up here and notice this pair relationship. So to do that, what should we put on first? Should we do the oxidation first, or should we put the bromine on first? Put the bromine on first because this is an activator, and all activators direct ortho and para. All right, so we'll do the bromination first, and then I'm going to say chromium this time. KMnO4 would work just fine too. One or the other is fine, and that does the oxidation. Right, so we didn't want to do the oxidation first because then we get a different relationship. Right, so the order in which you put things on is going to start to matter. Right, so that's kind of this next level thing we're going to start working on where, right, like that I gave you that assignment and said figure out how to make this. How would that work? This is a question on sampling about acidity. And it wants us to rank from least to most. So let's draw these guys out. They're all phenol derivatives, looks like. Nitro group on there. Another nitro group on there. Okay, so one of the first parts of this question people mess up. They don't know what it means, what acidity means. All right, so the first part we need to recognize is what do we mean by acidity? So what are we talking about here? Right, ability to donate a hydrogen. And specifically, what hydrogen are we going to talk about here? What's the most polar bond to hydrogen in all these? The OH bond. This OH, that OH, that OH, that OH. We're talking about that. So we're talking about essentially how reactive that bond is. That's what we need to figure out. The weaker the bond, the more reactive, right? The more acidic it would be. So if you just analyze these, right, you could say, okay, well, what do we got going on here? What's different about all these? Right? Looks like there's something in the pair position for all of these. One has nothing, one has this phenyl ring, and the other two have phenyl rings, but one has a nitro group in the meta position, and the other one has a nitro group in the para position. Right? So what you're going to need to do is one of two things. You can either draw resonance structures of the starting materials, or you could draw resonance structures of the actual conjugate base, or the O minus, and see how many resonance structures you can make. The more resonance structures you can make, probably the more stable it is. Right? So one thing I would look at right away, what do you guys know about nitro groups? So there's one way to easily start us off and at least find the least acidic. What do you guys know about nitro groups? Are they electron withdrawing or electron donating? Withdrawing, right? We can all agree on that. There's a plus charge in the nitrogen. So it's pulling away electron density. What's that going to do to the OH bond? Electrons are being pulled away. Is it going to make it more reactive or less reactive? Is it going to make it stronger or weaker if I'm pulling away electrons? More what? More reactive, right? I'm going to make this bond more polar. If I'm pulling away electron density, right? So I don't know which one of these nitros is the most acidic, but I know they're both more acidic than these two. So let's label them. A, B, C, and D, right? So I don't know which one's the most acidic, but I know it's between C and D. Right? We all can buy that, hopefully. Now let's go back and look at A and B here. Well, A has an H, and this is a phenyl. Well, what kind of substituent is a phenyl? Is it an activator or a deactivator, do you think? It's an activator, right? It can donate electrons into the ring, right? You could draw resonance structures where electrons go in. So is that going to make this bond stronger or weaker? If I'm pushing electrons in, is that going to make this H more delta plus? If I'm pushing electrons towards it, it's going to make it, I'm pushing electrons towards the H. That makes the H more plus. It makes that bond, right, maybe stronger. So B is going to be the least acidic. And then we know A is following afterwards. Everybody see that though? Think about, this is electron donating. You're pushing electrons in. That's not going to make this bond more polar, right? Because we're talking about how delta plus is H. I want to be pulling electrons away from H. I don't want to be pushing electrons towards it. So the more electron donating the group, the less acidic it'll be. Now what are we stuck with? Now we're stuck with C and D. How are we going to differentiate these guys? We can either look at the starting material resonance structures or the product resonance. What do you guys want to look at? Starting material resonance? Sure. Now, I'm gonna draw them all. I'm gonna draw a bunch of arrows moving at once, just because it's going to be easier to see, right? So the idea here is this: we have these nitro groups. Think of the nitro groups as it's the anchor that's pulling away the electron density. So we're going to try to push electrons towards it. And ideally, what we wanted to have happen, right? Those nitrogens have oxygens on them, right? If we could put a negative charge anywhere, where would we want to put the negative charge in this molecule? On that oxygen, right? Not a carbon. So one of these molecules is going to allow us to have a negative charge on an oxygen, and the other one's going to allow us to have a negative charge on a carbon. And it's up to you guys to figure out which one you think is more likely. Which one's better, right? So let's go. So I'm going to have the lone pair from oxygen come down. Pi bond goes there. Pi bond goes there. Pi bond goes there. Pi bond goes there. I can't push the electrons into the nitro, can I? I got to put these electrons right there on that carbon. So let me draw that. Plus. Boom, 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 boom. There, negative there. So what was I not able to do? I was not able to push, right? It didn't line up right. These electrons, I couldn't push those towards the nitrogen. Wasn't able to. Everybody see that? How I wasn't able to? But now let's look at the other one. Electrons come down, just like before, all the same steps. But now, I can push those electrons to that nitrogen and then kick up to that O. So now, I can draw a resonance form just like the one before, except, importantly except, to balance my charge, so now if we look at these two resonance structures here between C and D, which one looks better? Which one looks more likely? C or D? This is C, this is D. Which one do you like better? What are the differences? Both have O pluses, that's not any different. One has an O minus and one has a C minus. Which one do you think is more likely to occur?
The right.
The right. Notice, if this is more likely to occur, what happened to this, right? At the end of the day, we were still talking about what? Acidities. We were talking about how strong this OH bond is. In this case, where there's a plus charge on the oxygen, Do you think that bond's getting weaker or stronger? Weaker. And if there's a resonance form that's fairly happy because there's an O minus versus a C minus, which resonance form do you think is more likely? Well, this one. And this resonance form shows us that, right? Well, it's going to polarize that bond even more. So D ends up being the most acidic. Having that electron withdrawing group in the para position, everything lines up when you start pushing electrons around. Right? Now this is hard. This looks like a lot, right? What could you have done? What should I have done to make it a lot easier, make it better? What should you always do first? Number your carbons. Right? Number your carbons. You could draw in all the hydrogens, right? Because how many bonds can carbon have? 4. Right? It's always a good gut check, right? Because people will screw up this part right here. I can see where the mess up would happen. It would happen right here. People try to take this double bond, this pi bond, and jump it all the way over there. Can't do it. Can't do it. Right? Number thy carbons, draw on the H's, one step at a time. So this is the most acidic, and then the nitro group is the meta nitro group is the second most acidic. So let's do a Friedel-Crafts alkylation. So we're going to do a FC alkylation. And we always got to be worried about these ones, about rearrangements, right? We got to be concerned with rearrangements with these. So, well, I'll make it even easier for you guys. Well, no, I won't. Put a bromine on there. And I'm going to say our bromine's going to react with, we have AlCl3 here. And we have a chlorine. That's right. Like this. Alright, so we got Friedel-Crafts alkylation. So the first step, we got to identify the electrophile and nucleophile. In all of these ones, we also have to, what's the first step we have to do? So create that super electrophile, right? We got to have essentially the aluminum chloride, which is our best electrophile, right? Metal, is going to react with what in this case? Chlorine. So there it goes. Now I'm going to draw it the way it's in the book. This time I drew it a different way in class, but I'm going to draw it the way the book has it. Neither one is more right or more wrong, but I just want to make sure you've seen both. So you'll see the chlorine. In the class, I did it where when this chlorine attacked, it kicked out another chlorine. But I'm not going to show that here. I'm going to do a little different. So in this case, we got to balance our charges. So chlorine, this chlorine has a plus, right? It gave up electrons. You notice the electrons are going away from it. Who got electrons? What element? The aluminum did. So the aluminum actually has the negative charge. And now this throws people off. Because even though the aluminum has a negative charge, does that mean the electron density is actually on the aluminum? No, it's actually on these chlorines spread out over here. Okay. And that'll come into play in a second. Okay. So what's the next step here? Well, I kind of warned about it, right? The big warning is carbocations, right? So the next thing we need to do, right, in our Friedel-Crafts alkylation, the super electrophile is a carbocation. Right, so we got to make the carbocation. So I'm going to number our carbons now. Let's have these electrons go away. All right, go with the chlorine. So now where will the plus charge be? At carbon 2. And where will the minus charge be? Nope.
Still with aluminum.
Still with aluminum, right? Not yet. Right? The electron densities with the Cls, but the actual charge we have to draw it on the aluminum. And there's a sapling question. They use iron tribromide, but it's the same idea here. All right, so there we go. Have an electrophile, have our aluminum with a negative charge, balance our charges, but now we have a carbocation. So what's the problem here? What's going to happen? If it can rearrange, it will. And so right now we have a secondary carbocation. Can we rearrange to form a more stable carbocation? So what are we going to do? What kind of a 1,2 methyl shift, right? So you got make sure you know how to draw these arrows too.
Is that likely though?
Oh yeah. Let's see why. And it doesn't matter which methyl I choose. I chose 6. Doesn't matter which. So which new bond did I form between which 2 carbons?
6.
2 and 6. Good. Where's my plus charge at?
3.
Good. So now I had a secondary carbocation, and now I have a tertiary with 3 times 3 hyperconjugation buddies, with 9 hyperconjugation buddies. So that's pretty stable. So that's going to be my super electrophile. I can't make it any more stable than that, right? Okay, so now we have our super electrophile. Now we got to go back, right, and say, okay, we're all done with this mess. We got this guy and we got this guy. What's going to happen with this? All right, so maybe I'll redraw some of this stuff for y'all can buy where we're at. And you should know how to generate a super electrophile. We have Al, Cl3, and I'll put the minus charge there. So there we go. So now we're back to, what do we need to do now? Now we need to take a look at our nucleophile, right? So this is certainly our electrophile. Now we got to look at our aromatic system. And we got to say, well, now it's not just a benzene ring. Now we have a bromo substituent. So we know bromines are deactivators, but there's no other thing on the ring, so that's the only thing that really matters here. But where do bromines and all halogens direct normally? Orthopara, right? They're the weird ones, right? They're the weird deactivators because they still have lone pairs, and we drew those resonance structures out where there's a negative and a negative here, right? So they still direct ortho and para, but now we have right? So now we have 2 choices. Are we going to get any ortho, or is it going to be mostly para? Is it going to be no ortho or no para and mostly ortho? What's going to be the decision here? What's going to determine that? What do you think would matter? What's the difference between ortho and para in relation to the bromine? Ortho is closer or farther away? And para is farther away. And bromine's decent size, and this is kind of a big chunk of carbon. So where do you think you'd rather put it? Probably para because of sterics, right? Absolutely. So let's do that. We should number our carbons again. Let's do 1, 2, 6, 3, 4, and 5. And what should I do? Should I do numbers or letters on the ring? Sometimes it's nice to do letters. A, B, C, D, E, and F. So which lettered carbon should end up bonded to carbon 3? Which letter? D. Very good. So what H is going to be replaced? The H on which carbon? D. The H on D. Remember, this is a substitution reaction. Somebody's going to do it. Somebody's going to try to take the H off of E. I promise. I've seen it already today. Right? And now who has the plus charge?
E.
E. Very good. Plus charge. Number my carbons. 5, 3, 4, 2, 1, and 6. D, E, F, A, B, C. So now it comes back in our the AlCl3 needs to be regenerated. So there's a negative charge in aluminum. And we need to lose the H, which H is it? The H on D. Look at that long bond I drew for us. Alright. And I know people had trouble with this in the homework, I've seen it a couple times. Where the electrons actually come from that grab that H.
From the bond.
They come from the bond, right? Because you're making HCl, and aluminum needs to lose electrons. So the electrons can't come from the chlorine's lone pairs. It needs to come from this bond. Right? So you need to take the 2 electrons from this bond to take that H. And then those electrons in that CH bond go between D and E here to reform that pi bond. All right, so that's been why people have been messing that up. Reformed.
You're saying the bond grabs the H, right?
The bond grabs the H, right? The bond is attached to the chlorine, right? So one of the other byproducts, right? We made HCl. Hopefully, we agree with that. We made AlCl3 again, and we made this substituted benzene ring. We're gonna show how to do. If you wanted to make a benzene with a straight chain alkyl group off it, what are the processes, what are the possibilities to do that? So let's say if our target, so we're trying to make this, and I'm going to mix it up, and I'm going to throw, don't want to mix it up too much, I'll throw this in there too. And we want to make this from benzene, let's say. How are we going to do that? So let's take a little bit of time and look at that for a bit. All right, so we're taking a chance to look at this. So the first thing we want to do is we want to stop the inclination to start from the starting material and try to work this way. You got to stop ourselves from doing that. That's the first step.
Priority as to what you want to add first, as far as the bromine or the.
There will be priority, and that's what we need to talk about. So there will be priority of which goes first and which goes last, and all those kind of things. What we do. So the first thing, let's just analyze the product. So the product has two substituents on it. The bromine is a bromine an activator or a deactivator?
Yeah.
So the bromine's a deactivator. And which way does it direct? O and P. Right, so I like to write these things down and just say like, okay, what do I know? What about then the other thing we have this chain, is that going to be an activator or a deactivator? It's going to be an activator, and which way does it direct? All activators direct orthopara. That's right, so I've analyzed my substituents, but now here's the issue. So they're both orthopara directors. Cool, we're right there. What's their current relationship to each other? They're meta to each other though. So, but they're meta. So that means one of them at one point was a meta director. Had to be, right? How else would you get these two things meta to each other? Right? One had to be a meta director. So let's look at the two substituents. Well, do you guys know any ways to change the bromine to do something, to be something else? I don't. But do you know a way this could have came from something different? What could this have been first? A acyl group or just a ketone. And if it's a ketone, so let's take one step back. Right, so retrosynthetic arrow, one step back. Let's pretend that initially this was this. And the bromine was there. Now, what is this? This ketone is an activator or deactivator? It's a deactivator, but in which way does it direct? Meta. So what thing did I put on? If I go one more step back, what part had to come on first? The ketone or the bromine had to come on? What had to come on first? The ketone had to be on there first. So I'll just take the bromine off. Right, because the ketone had to be there to make the bromine go meta. And then can you make the ketone from the regular old benzene ring? Hope so. right? So you see is kind of how we could break these things down. So let's go forward and double check our work. So going forward synthesis, right, with that kind of arrow, we need, how many carbon pieces are we adding?
3,
1,
Four.
2, 3. No, what? Go ahead and number them. 4. And we can do A, B, C, D, E, and F. Right? So you need to add a 4 carbon piece. So it's going to be a chlorine attached to the carbonyl. 1, 2, 3, 4. And we need a catalyst too. Let's throw that aluminum chloride in there. AlCl3. That'll put the ketone on. Good to go. Ketone's a deactivator, and we know it directs meta. That's that kind of deactivator. So what kind of reagents are we going to need to get the bromine on? Br2 and FeBr3 work. Good. Now the bromine's on there. And now, in this case, you have 3 different options, right? Because what do we need to do? Now we need to reduce this carbonyl to 2 CHs. And that's where we have those 3 different options. We have the acidic, the basic, and the neutral. We have the Clemenson, the Wolff-Kishner, and the palladium on carbon, H2 palladium on carbon. So any of them work in this case, right? Because there's not really a lot of other substituents around to react with, right? But I warned you guys about what I warned you about. HCl can react with other pi bonds, right? Alkenes and alkynes. OH minus is a strong base. It could react with carboxylic acid, right? Do different things. H2 palladium on carbon will do what to an alkene or an alkyne? It'll reduce it. It'll also reduce nitro groups off of benzene rings. It'll also reduce nitriles off benzene rings. It'll reduce benzylic carbonyls too, which we're doing here. So the types of reagents, and there's no preference in this case. So you could have zinc, HCl would work. You could have the H2NNH2, that would work with OH minus. So 1, 2, and then you could have H2 palladium on carbon. All 3 are possibilities, all 3 work. That gets us there, right? Because again, this is that benzylic position, right? This benzylic carbonyl, we've identified the benzylic carbon as an important position for benzylic reductions, benzylic CH oxidations, all those things. So a good thing to maybe think about, just to clarify about some of these benzylic oxidations, that I want to make sure people understand that there's 2 possible options. There's usually chromium reagents, CrO3 is one, or, which works just as well, something called KMnO4, which might be called permanganate. But the best way, right, I think, to remember what's going on here, first you need to remember, does that place, are there benzylic CHs? If there are no benzylic CHs, such as here, there's no benzylic hydrogens, that position can't be oxidized. So they're focused on benzylic CHs. If there's no benzylic CHs, this oxidation can't take place. But how to remember what these reagents do? It's an oxidation. Notice a lot of oxygen, right? So either one of these reagents work. If you see KMnO4 or permanganate or chromium, CrO3, oxidations. So the final product in this case, the 2 positions that have benzylic CHs, those carbons become carboxylic acids, and the other one just stands put. But oxidation's oxygen. Benzylic CHs. Has to have the benzylic CHs.